It's a 1016 Cougar. Oh, and you're welcome to bring 1 page of notes along to the exam. You can write on the front or on the back or on the edge and so forth. Size is 8.5 by 11. Okay. Well, today I'd like to wrap up our discussion of diodes. I'll spend a small amount of time talking about capacitors, and I hope to start talking about MOSFETs by the end of the period. So we spent the last 2 periods talking about a diode, and we observed that if you have a diode, it's a nonlinear device. And the tools we have to analyze circuits with nonlinear devices are different than the tools we oftentimes use to analyze linear circuits. Some of these things that we derived for linear circuits, like current divider and voltage divider equations and so forth, don't have a corresponding counterpart if the circuit is nonlinear. So you pretty much have to go back to Kirchhoff's laws and do nodal analysis, or I guess you could also do a mesh analysis if you so chose. We also, at the end of the period, summarized the models that we had last time, and we found that we had 4 different models for the diode. The most complicated one is the upper left. That's the diode equation model. And then we had a piecewise linear approximation with some slope. And then we had a piecewise linear approximation in the upper right, where we assume that the slope is infinite. And on the bottom, we have the ideal diode model. And then we asked the question, which model should be used? What was the answer to that? What was the answer to that? What?
Simplest one we can.
Simplest one you can get by with. Okay, I like that, right? But what's the challenge with knowing what the simplest one is that you can get by with? Yeah, you analyze it with that model, but how do you know that it's accurate enough? Well, one way to know is to go to the more complicated model and analyze it. If you get the same results, then you say, well, the simpler model is good enough. But then why did you mess with the simpler model? Because you had the more accurate one. Or if the simple one, the more accurate one, give about the same results, how do you know they're good enough? So you might go to the next more complicated model and see if they agree. And eventually when you get done, you're at the diode model, right? The diode equation model. So you might as well start there in the first place. Make sense? So we want to see if there's a way that you can determine whether the simple model is good enough without going to a more complicated model. And here were the models that we had mathematically. This time I've got them listed from the simplest one to the most complicated one. So if you want to know whether this model, for example, is good enough, you can go in and put in, in fact, if you want to know if this model is good enough, you can put in 0 and 0.6 volts, and if the results are about the same, then the top one was good enough. And it's not too hard to go to this model. If you want to know if this one's good enough, a good test, that's the second piecewise linear model, put in 0.6 volts and 0.7 volts. That's a real big range in currents that would result in that from the diode equation. And if you don't get much difference in the results when you put 0.6 and 0.7 in, then that model's probably good enough. But you've solved the problem twice. You solved the problem twice. But solving a simple problem twice is oftentimes much easier than solving a harder problem once. Make sense? Okay, so, and this strategy is used a lot, not just in diode circuits, but for other models as well. So, let's now comment on how we're going to solve these nonlinear circuits. And also verify that the model is valid. So I'm going to try to determine I out in the following circuit. I'm going to assume a piecewise linear model with VD of 0.6 volts and RD equals 0. I'm going to guess the state. I might guess wrong, but if I guess wrong, I won't eventually get the wrong answer. I'm going to analyze the circuit with a model that I had used, and then I'm going to validate the state that I guessed was valid. And then I'm going to assume piecewise linear model with 0.7 volts. I'm going to guess the state of the diode. I'm going to analyze the circuit with this model, and then I'll validate the state was valid. If I guessed wrong here, then I'll go back and guess again, because it won't validate. Then I would guess the off state. And of course, there's only two states in this model. So I'm going to have to, I can guess wrong once. But if I got the wrong state, it has to be in the other state. Okay. So then I analyze what's now the correct state. And that gets me down to the same point right here. So let's go through an example and do that. So here's our circuit. I'm going to guess the diode is on. That's the guessing the state. Now, if you look at the model and you're guessing the state, we have two regions here. This was 0.6. This was the off state. And this was the on state. So when I guess the on state, I put in the model for the on state. And in the on state, there's 0.6 volts across it. So I put in 0.6 volts for the diode right here. And then I analyze the circuit. And the current is 12 minus 0.6 over 10K, which is 1.14 milliamps. Now I've got to validate the state. And the conditions for the diode being on was what? What was the condition for the diode being on? We had the equation that says ID is equal to 0 if VD is less than 0.6 volts and VD is equal to 0.6 volts if ID is bigger than 0. So here's the model and here's the condition, right? So we guessed it was on, and if it's on with 0.6 volts, what's the condition for it to be on?
Positive current.
Positive current. So to validate the state, we have to show ID is bigger than 0. Well, we have ID. ID is 1.14 milliamps. So do we validate that state is valid? Yeah. Don't know the model's valid yet, but if the model's valid, the state's valid. So what do we do next? What we're going to do next then?
0.7 volts.
Yeah, 0.7 volts. So we guess a different model. So we'll put in 0.7 volts. We're going to guess this on again. So I analyze this circuit. I put in the 0.7 volt model, analyze this circuit. The direct output current is 12 minus 0.7 over 10K. And it's 1.13 milliamps. I need to validate the state. To validate the state, I have to show what? Current's positive, which it is, so the state's valid. Now we have to validate the model. And to validate the model, we have to do what? Show that the difference between the two solutions is small enough that we don't care about which one we use, right? So one solution was 1.14 milliamps, one solution was 1.13 milliamps. They differ by less than 1%, probably good enough. Okay. So pick either one. We don't know which is better, whether it's 1.13 or 1.14, but it probably doesn't make much difference. Make sense? Look at another example. Same as before, except I'm going to reduce the supply voltage to 0.8 volts instead of 10 volts. And I'll use the same strategy. So, I'm going to guess the on state. Now, it happens to be beneficial to guess the correct state if you can do it. Because you don't have to solve the problem again after you found out that the state didn't validate. So some rationale behind it. Let's just back up just a bit. It seems like that we're trying to have a positive voltage here, which means we're trying to push current out of the supply, means we're trying to push current in this direction, and the diode tends to be on when you push current from the anode to the cathode. So that's the rationale behind guessing that the state was on. So now let's go back to the second problem. We'll put in the model of 0.6 volts. Calculate the current. 0.8 minus 0.6 over 10K is 20 microamps. To validate, we have to show what?
0.7 model.
What?
That the 0.7 model.
We're not going to justify the model yet. We're just going to validate the state now.
Oh, that's bigger than 0.
It has to be bigger than 0, and it is. Okay, so the state's validated. Now we're going to validate the model. So yes, or put in the model with 0.7 volts. Assume it's on. Calculate the current. 0.8 minus 0.7 over 10K is 10 microamps. Validate the state. This is positive, so the state validates. But is the model good? Well, we have to see if the difference in the two solutions is very big. In this case, one solution was 10 microamps and one solution was 20 microamps. So were we justifiable by using a simple model? No, we have 100% difference in two solutions. So since the difference is not small, let's use a different model. In this case, you need to go to the diode equation. If you put the diode equation in, we can again use Kirchhoff's voltage law. The output current is equal to this voltage minus this voltage divided by 10K. I guess that's Ohm's law I used there. And then the diode here has the relationship between the current and the diode voltage. I diode, which is I out, is equal to IS e to the VD over VT. Now all I have to do is solve these two equations. Well, that's easy to do. I can eliminate VD between these two equations, solve this one for VD and stick it into here. But what happens when I do that? It's an implicit solution. Implicit solutions aren't hard to handle though by iteration or in MATLAB. Everybody's familiar with MATLAB, right? Okay, so you go to MATLAB and very quickly get a solution to this. You can iterate on your computer to get the solution. If you do that, you'll find that I out is equal to 18.6 microamps. Coincidentally, in this case, it happens to be between the two solutions we had before. Doesn't have to be, but in this case it was. Okay. And assuming this is the model, then this would be quite accurate. Any questions? So we're analyzing actually fairly complicated circuits in a very systematic way.
So one thing, why were you? How can you assume that an I source is one femtoid?
Oh, you don't have to assume that. When I said IS is equal to 1 femtoamp, that has to be obtained from the characters of the diode. Okay. There's no that's predetermined when the manufacturer took place of the diode. Okay. So here's a summary of the process. And in some cases, we don't have to verify the model. Sometimes we only have one model. If you only have one model, you only have to go through this once. You don't have to verify the model. So again, you guess this applies anytime you have a piecewise model. The model we have for the diode here it's piecewise linear. Both segments are lines, right? But we could have a piecewise nonlinear model as well. This applies to any piecewise model. Guess the state of the device, analyze the circuit, verify the state, and then repeat steps 1 through 3 if necessary if the verification fails. If you have more than one model, you have to go through this process again to verify the model is valid. So, in summary, what's happened is we've solved a problem twice, but we typically dramatically simplify 2 analyses rather than have a much more complicated single analysis. Oh, here's another example. Here's a diode circuit, and this circuit we're going to use a piecewise model, and I'm going to have time varying inputs instead of a static input. Now, I'm not going to verify the model here, but if you look at what happened in the previous case, when we had a big voltage in that circuit relative to the 0.6 volts on the model, the simplified models apply. When we had a small voltage in relative to the 0.6 volts, the simplified models introduce a lot of error. So here I've got a sinusoid that has a value going between minus 80 volts and plus 80 volts. Are we putting in a small signal or a big signal relative to the 0.6 volts? Really big signals, right? So I'm going to assume that our piecewise model is valid here. In fact, I'm probably even going to assume that the ideal model is valid. Because whether we look at a 0.6 volt in a model or 0 volts in a model relative to 160 volt swing probably doesn't make much difference.
But isn't there a point in that sinusoid where it's very small? Wasn't that?
Yeah, good point. So it might be the case that for a small portion of this range, we don't have a real good solution. Good observation. So if you look at the sinusoidal signal that goes between plus 80 and minus 80 volts, maybe 1% of the time, maybe our model's not real good. Make sense? Good question. So after we get the solution, we'll go back and see what the implication of your question was. So I want to determine V out. Now, if the input's time varying, we'd expect the output to be time varying as well. So I'm going to guess that diode D1 is on. And so I can put in the model for the diode. Since it's an ideal model, when it's on, it's a short circuit. And the diode current is the current flowing from the anode to the cathode. So you've got to keep track of the orientation of that current. If I would have put the 0.6 volt model in, I'd just have a 0.6 voltage source here instead of 0 volts. So here's the circuit. And I want to obtain V out. Oh, the solution is easy in this case. A lot of times it is. What's the solution? What's V out? What? V in. Output appears across the input. Doesn't depend on these resistor values. So V out equals V in. Solution's easy. Now I need to find out where that solution is valid. Where's that solution valid? It's valid provided the diode's on. That is, it's valid provided that ID is bigger than 0. So now we've got to calculate ID. ID in this case, ID is going to equal V in, which is 80 sine of omega t. What was it, 500? Is that what I had? 500 t. It's this voltage divided by 1K, right? And this has to be bigger than 0. for this solution to be valid. So let me plot now a portion of our solution. So here's our input. I'm only going to draw one period. And this height is 80. And this is minus 80. And the output is equal to input on this curve, provided that this quantity is positive. That is, provided this quantity is positive. That is, provided that 80 sine of 500t is positive. Well, in this region here, it's positive. So this solution is valid in this region here. I don't know what's going on here yet. But this solution is not valid there, because here the current would be negative. Make sense? Now what do we do? Guess the other state? And it can be one or two states. So in this other case, we're going to be we're going to know that we're going to get the rest of the solution when we guess the other state. We guess it's off. If we guess it's off, we have an open circuit there because we have an ideal model. The voltage from anode to cathode is from here to here. And now we have to solve it. And what's the output in this case? This is a nonlinear circuit. Can I use linear circuit principle to solve this circuit?
For the simplification.
Yeah, once we simplified it, it's now linear, right? So it's linear, so I can use voltage divider equation. And the output voltage is Vn over 2. So V out is equal to Vn over 2. So I'm just going to do this off the side. Here's Vn. And V out is equal to Vn over 2. So it looks like this dashed line here. It has to be valid for the things that we didn't have here before because there are only two states. So we know then that in this part here, it's going to look like this. But let's just be formal about that. V out is equal to Vn over 2, so it's 40 sine of 500t. The dash curve I drew up on the other upper left-hand side of the board. It's valid for, in this case, for Vd less than 0. That was a condition for it to be off. And so Vd is equal to Vn over 2. So it's valid for Vn less than 0 then. So here's a mathematical expression for the output of the circuit. Make sense? What about circuits that have more than one diode in them?
You use superposition in that case?
What?
You use superposition in that case?
No. Simple question, simple answer. And why can't we use superposition? It's a good question. It's a good comment. But why can't we use superposition? Nonlinear. We X out things that don't apply for nonlinear circuits, so we can't use superposition. So what we're going to do is, and if you look at the circuit, we've got a big voltage here. So I'm going to assume a piecewise model for the diode. And since that voltage is so big, I'm going to assume an ideal model for the diode. Make sense? So each diode can be in one or two states. So how many different states could we have here? 4. Both diodes could be on, both diodes could be off, The first one could be on, the second one off, the second one on, the first one off. Okay. So now we know what different states can exist. Now in any of those 4 states, the circuit's going to be what? It's going to be linear, right? Because we're going to put in a piecewise linear model of the device. So can somebody suggest a strategy? Guess a state, solve the circuit, and then verify that state is valid. That is, verify the condition on both diodes is what you guessed. We get the wrong solution by doing this if you guess wrong. Not eventually. If you guess wrong, the state won't validate. And that just means you have to guess again. So we won't make a mistake solving the problem, but if you guess wrong, it may take you longer to get to the solution. So, this voltage source is trying to push current in this direction. So I'm going to guess diode 1 is on. But I'm not exactly sure what's going on. This is trying to push current in this direction as well. So they're both trying to turn this diode on. This one's trying to turn this diode off. So it looks like that maybe the first diode is on and the second diode is off. I can guarantee that it's easy to create circuits. When you look at it, it's not clear what the state is, because you can get them real close so that you're just at the border of transition from one to the other state. So I'm going to first guess diode 1 and diode 2 are on. We'll see if we get lucky there. If diode 1 is on, put a short circuit here. I have ideal diode model. Diode 2 is on, we put a short circuit there. The currents from anode to cathode are labeled on the thing here. So we solve the circuit, and then we have to show what? The state's valid. ID1 has to be positive then, and ID2 has to be positive. They both have to. So in this case, the output is equal to minus 20 volts. Is that clear? This is at ground. This voltage here is minus 20 volts then. So the solution's easy. If the output is minus 20 volts, this voltage here is minus 20 volts. That means the current is flowing in this direction here. This is 0 and this is minus 20, so this current's going to go this way here. And how about this current here? Well, this current will be the difference between this current and this current. So we have to get those two currents and subtract the two. So ID1 is equal to ID2, excuse me, we said it was 20 volts divided by 4K, which is positive. And ID1 is 80 volts over 1K, it's this current, minus the current ID2, because ID2 is flowing in this direction, and it's 85 milliamps, so it's positive. So I guess our solution is valid. And in this case then, V out is equal to minus 20 volts. Okay. If I would have guessed any of the other three states, I would have not validated, and I would eventually get here. A couple more comments about diodes. There are a lot of different diodes. We could spend the whole course talking about diodes. So here's some of the diodes that are around along with their symbols. We have signal or rectifier diodes, and really the diodes we've been thinking of so far are in the class of what we call signal or rectifier diodes. Oh, there's one thing about diodes I didn't talk about. I should mention it briefly before we go on. If you look at a diode, the diode equation suggests that the IV characteristics of a diode I don't care whether you use a piecewise linear model or the diode equation model. The current increases rapidly if the diode voltage is positive, and the current is equal to negative IS, a small negative value, if the diode voltage is negative. A real diode will have a breakdown that occurs back here. And that's a specification of the diode. They're manufactured for different breakdown voltages. So we ignored the breakdown voltage of the diodes here. If you're working with large voltages and you put it into breakdown and you don't have a serious current limiter, when a signal or rectifier diode breaks down, it usually destroys itself. Because you have a big voltage across the diode in the negative direction and a lot of current flowing. So the power dissipation gets high very quickly. Okay. We have pin or photodiodes. Now, your signal to rectifier diodes are just typically a silicon junction. But you can use other materials to make diodes as well. With some materials, when you make a diode, we have current conducting or current flowing through it in the forward bias direction, it emits photons. And you have other diodes, even silicon diodes will do that. If you shine light into them, you will change the current IS. Now, on most diodes, you put your PN junction in an opaque case, so light doesn't get into the diode. But if you put your diode in a transparent or translucent case, light can get into the diode, into the junction. And silicon is actually, if you look at a silicon wafer, it looks like silicon is opaque, doesn't it? But actually, at the wavelengths of light, or at least some wavelengths of light, silicon is not opaque. So it's easy to get light to flow into the junction if you don't enclose it in a case that keeps light out. When the light or those photons get into that depletion region, they cause current to flow. Is that good or bad? It's bad if you don't want the light to affect the carrier circuit. But if you have a fiber optic cable and you're transmitting digital information across a fiber optic cable, when you shine light in the cable, maybe 10 kilometers away, you want to see if there's light coming in or not. If you had a device that responded to light, you use that as a detector. So pin diodes or photodiodes are widely used in fiber optics applications. It happens that they operate extremely fast. You can get pin diodes that operate in the gigahertz or tens of gigahertz range. So you shine a light in a cable, in a fiber optic cable, and boom, somebody has the other end of that cable. You put a pin diode on, you put light in here, you'll see it the other side. If you could toggle it at 5 gigabits per second, you've got a channel that's operating a data rate of 5 gigabits per second. Make sense? Okay, so pin diodes or photodiodes, they are designed so that they intentionally respond to light. You shine light in at the junction. Light emitting diodes. So if you take different materials, you put current through the diode and it emits photons. Light emitting diodes are used for a lot of things. A lot of displays use light emitting diodes. In fact, in the last 5 years, the incandescent lights have pretty much been replaced now with light emitting diodes. Zener diodes. We said that one undesirable property of a rectifier diode or a signal diode is that if the voltage across it gets big and negative and you exceed that voltage, you'll break it down and destroy it. Some diodes are designed so that breakdown voltage might occur at minus 5 volts or minus 8 volts or something like that. Those are called Zener diodes. And this breakdown is real steep. So if this breakdown is at minus 5 volts, then you will intentionally push current through it in the back direction to create a voltage reference of 5 volts. So Zener diodes are oftentimes used to make voltage references. Okay. Varactor or varicaps. That depletion region of a diode thickness changes as the amount of the reverse bias on it. It even changes a little bit under forward bias, but certainly under reverse bias it changes a lot. If you have a depletion region separated by 2 conductors, we have what? A capacitor. And if you change the voltage across the capacitor, you change the capacitance. So a lot of electronic circuits are tuned by changing the DC voltage across a diode. Diodes that are designed to operate that way are called varactor diodes or varicaps. Schottky barrier diodes. Schottky barrier diodes typically are much faster than pin diodes or photodiodes, and they have much lower voltage drop across them when they're on. Okay. So we have a lot of different diodes with a lot of different properties. One other comment about some of these other diodes. If you go back to the work of Shockley and what was the other guy's name? If you go back to the junction diode, they were interested in using it as a rectifier. And a lot of these other properties, the fact that you shine light on it and the reverse current changes, we don't like the large reverse current normally. You put current through it and the light comes out. Those would probably be considered to be undesirable, and the capacitance across the changes, those would probably all be considered to be undesirable properties of the original diodes. But engineers are clever. If you find a property that's undesirable enough, a lot of times you'll find an application that exploits that undesirable property. Or the process people will then look at ways to enhance that undesirable property to make it a useful property. Okay. So keep your mind open when you see something that you don't expect, and ask the question, even though it's not what I want for this application, is there another application of this undesirable property that makes it very useful? Any question about diodes? We're not going to spend much time with capacitors because we already talked about capacitors a little bit. 3 types of capacitors: parallel plate, fringe, and junction. Parallel plate capacitor, we have 2 conductors and an insulator in between. We typically, if we make these as capacitors, we'll make the one plate bigger than the other plate all the way around. There's a distance d between. The area of the intersection of the 2 is what's of interest here in this capacitor. So here we have the top plate on this drawing, smaller than the lower plate, and the capacitance that we get is the dielectric constant of the material between, which is called the dielectric, times the area divided by the distance between the 2 plates. Okay. And these are the type of capacitors you work with in 230 lab. Most of the capacitors of 230 lab were made this way. You make a big plate, you out of foil, put a thin plastic film between, roll it up and dip it in plastic, and hopefully you don't short anything out, and you call it a capacitor. Okay. Now, we typically will rewrite this equation by putting epsilon over d together, and we call that the capacitance density. So in the technology files we've been looking at in this course, instead of giving epsilon and d, they typically give the capacitance density. So you just multiply the capacitance density by the area to get the total capacitance. Fringe capacitors. The upper levels of metal we saw were real thick. If the upper levels are real thick and you put them close together, you get a capacitance running laterally between the upper levels of metal. You may still have silicon dioxide as an insulator, so they can make very good capacitors. So these are called fringe capacitors. Now sometimes you have fringe capacitors you don't want. Sometimes you'll have a trace running here and another trace getting close to it. Then it's the parasitic we talked about earlier. It's also a fringe capacitor. But a lot of times we will make, if we want to make capacitors, one way we make capacitors is to exploit this property, and we do layouts where they're close together, and then we rely on this lateral capacitance as a fringe capacitance. And here might be a layout of a fringe capacitor. So you take two conductors, pretty thick, and have fingers going between them. And what this does is it gives you a large cross-sectional area then to get the capacitance up. Junction capacitors. We have a PN junction, we said we have a depletion region in between. And you can show that the voltage dependence of that capacitor is equal to Cj0, some constant, this is the character of the process, divided by 1 minus Vd over phi b to the nth power, where Vd is the voltage you put across the capacitor, and phi b is a constant as well. Phi b is around 0.6 volts, and n is about 5. This is about 0.5. This is about the square root. So you can see as you change Vd, you'll change that capacitance. We had another name for those. We talked about them in diodes. What do we call it? Was the diode when we were using it as a capacitor?
A varicap.
A varicap or a varactor diode, right? But they always exist when you have a PN junction, even if you don't want them. But if you want to make a voltage variable, you can easily do it. So if you want to control the size of that capacitor, you can control it two ways: by the area or by the voltage you put across it. Now this is square root of quantity here. So if Vd was large and positive, then we'd be trying to take the square root of a negative number, right? But usually we don't forward bias the PN junctions in MOS transistors because we don't want current flowing through them, so we reverse bias it. So normally Vd is negative, and we take the square root of a positive number then. But Vd can also get positive up to about theoretically up to plus 0.6 volts, which is phi b. This equation is pretty good for a forward bias up to about 0.3 volts. Let's plot that voltage of the varactor diode. So if you plot the voltage here, it looks something like this blue curve. This is not a sketch, this is a plot. And what we see is that when we change the voltage from 0 volts to minus 4 volts across it, we change the capacitance by about a factor of 2. So is this a little bit of adjustment or a lot of adjustment you can get with this voltage? It's a factor of 2. That's a lot of adjustment. By changing the voltage, you can change the capacitance a lot. In some cases, we want this to happen. In some cases, it hurts us. Let's talk a little about MOSFETs. We've got time to get started at least. So we'll try to give a little bit more of a qualitative discussion now of how a MOS transistor operates and come up with a better model for the MOSFET. All we have right now is two models. The two models we have are what? The switch level model, and then another switch level model with a resistance in the drain. So now we're going to try to get a better model of the device. So here's a three-dimensional cross-sectional view of the device, and the drain, the gate, the source, the width, and the length are all shown on there. Since you guys have been in the lab now for a better part of a month, we should pretty much understand how we make these devices in the laboratory. And the materials that are used, this is an N-channel MOSFET, so N diffusion, P substrate. What's this around here? Depletion region, because anytime you put the P and the N junction together, you're going to have a depletion region. So you got a depletion region surrounding the devices, gate oxide, an insulator here, and a conductor on top. Okay. So now let's look at a situation where we apply a small gate to source voltage to the transistor. And VDS, I put a voltage from drain to source, I'm going to assume right now it's small, and a bulk to source voltage right here. I'm going to connect to the bulk here, I'm going to assume that voltage is small as well. If I put a positive voltage on the gate, I'm trying to pull electrons to the surface. And so what I'll do is I'll end up creating a depletion region underneath here, because it started out p-type, and I'll succeed in pulling some electrons near the surface, and that will ionize that region underneath the gate. There's no current that's going to flow because to get from here to here, we've got a reverse bias junction here, and we can't get through here either because there's just a depletion region there. So the drain current is going to be 0. This depletion region here now is electrically induced. We put the positive voltage in the gate, and that formed that depletion region underneath the gate in the channel region. So the 3 currents are 0. No drain current, no gate current, no bulk current. And this is turned the cutoff region of operation of the device. If I increase VGS, what am I going to do? Pull harder on those electrons and increase the depletion region. But nothing's happened yet. We still have no current flowing. So this is the model in cutoff. Pretty simple model. Now I'm going to increase VGS even more. And I will succeed in pulling enough electrons to the surface that I will create what's called an inversion layer here. Once that inversion layer is created, now I have a conduction path from drain to source. So I'll get a little bit of current to flow. And if this is a uniform layer here, it will form a resistor. We have a special name for a resistor that's very thin like that. What does it form?
Thin sheet.
What?
Thin sheet, thin film.
Yeah, thin film, so we call it a film resistor that we form here. It's a thin resistor. And we can model the device here as the drain current is equal to the channel resistance, the resistance in the channel, times the drain to source voltage, because there's just a resistor between here and here. The critical value of VGS that creates this inversion layer is called the threshold voltage. As long as the gate source voltage is less than the threshold voltage, you'll have a depletion region. But as soon as you exceed the threshold voltage, you've got this inversion layer there. Okay? So that's the critical parameter of the device, the threshold voltage of the transistor. And the model for that, if you increase the length, it should go up linearly. If you increase the width, it should go down as a reciprocal to width. And when VGS goes to the threshold voltage, it should go to infinity. And then don't worry about where it comes from. There's a process parameter, UCOX, that will be used to complete this equation. So I could say then that ID, if this is the resistance, is going to be the reciprocal resistance times the voltage. So it's going to be UCOX, W over L, times VGS minus VT times the drain to source voltage. And here's a model for the device. So it behaves as a resistor between drain and source. And this is what we call deep triode region of operation. The term triode comes from the corresponding operation of vacuum tubes. They have properties very similar, electrical properties very similar to those of a MOSFET. Physical properties very different. The electrical properties very similar. this is an interesting resistor, because this is now a voltage-controlled resistor. As I change the gate to source voltage, I change the resistance. Is that a neat device? There are a lot of applications for it's the alternative to going in and turning a resistor or sliding a sliding a wiper on a resistor. We can control it with the voltage. You can control it with a computer pretty easily by having a digital to analog converter and letting that analog output control a resistance.
Wouldn't it stagnate at one point?
What do you mean stagnate?
Won't increase as you increase the current?
This is under the assumption that the drain to source voltage is pretty small. If the drain to source voltage gets bigger, then different things happen. So here's if you make the gate to source voltage bigger, of course, this layer gets thicker. Now, if you start increasing the drain to source, give me 1 minute and we'll stop. If you increase the drain to source voltage, then the voltage from the gate to the channel will decrease near the drain side. If it decreases, the inversion layer will start to thin. And instead of having this uniform film, we'll have a trapezoidal shaped film. Okay? So that's what you're referring to is going to happen. We're still in the ohmic region, but now the device is becoming somewhat nonlinear. Because as we change the drain to source voltage, the resistance is changing on us. So it's no longer a very good resistor in this region. So this equation no longer applies, and we can replace that equation by this equation here. And all we're doing is including a small drain to source dependence on the current now. Of course, as VDS goes to 0, as VDS is small, it reduces to what we have in deep triode. So this is called the triode region model. It applies in deep triode, and it applies until you make the gate to source the drain to source voltage big enough that the channel pinches off. And that's what happens here. Okay? If you increase the drain to source voltage more, nothing happens in here. The device saturates and the current stays constant. And it stays constant at the value that we had when it pinched off. You're going to have to wait till Monday to find out what that value is. Are there any questions? Reminder, exam on Friday, review session on Thursday night. Oh, if you want to pick up your graded homework, it's right here. I apologize for not passing that around. Thank you.